Okay, fine. Okay, so maybe what I can do, because I didn't start the recording, what I'm going to do, I'm going to summarize it again. Okay, fine. So here, what we are trying to do, we are trying to develop a theorem for, continuation of a unique solution. Okay, continuation of a unique solution. So what we are going to do, we are going to prove that, if this initial value problem, if I am giving this initial value problem, okay, where obviously, I'm going to consider, say, suppose an open rectangle R, where this point x0, y0 belongs to. Okay, so then what happens? Obviously, if f and fy are continuous, I can get a unique solution of this initial value problem 1 in the interval I1 given by this, where x1 is strictly greater than 0. Okay, fine. So then what we have to do, I have to prove that I can extend the solution in this interval to the interval given by something like this. x0 plus h1 plus h2, where your h2 is strictly greater than 0. Okay, so that is what we are doing. And again, let me recall what we did. So now we are assuming that phi1x is the unique solution of 1. Okay, so then this will be my pictorial depiction of the solution phi1x here. Okay, you see, this is my x0. Okay, and your open rectangle is there somewhere. Open rectangle is there somewhere. Say open rectangle may be something like this. Okay, which encompasses this point x0, y0. Okay, fine. So now this is x0. If this length is h1, obviously this point is x0 minus h1. This point is x0 plus h1. So if I assume that x1 equal to x0 plus h1, obviously, this length is simply phi1 x1. Okay. So now what I am doing, I am constructing a new initial value problem given by this. Okay. So as you can see, under like say, as we already know that at least this solution of this, that is phi1, it extends at least up to the point x0 plus h1, right? Which I am designating as x1. So your phi1 x1 must be equal to y1. Is it okay? That is where before recording, I told you, right? So now, if this point x1, y1, it also lies in the open rectangle R, then what is going to happen? Because f, fy, they are already continuous in R, I should be able to find an h2 strictly greater than 0 and h2 strictly greater than 0 such that a unique solution of 2 exists in the interval. Is it okay with everybody? Fine. I'll give you a pictorial. Fine.
Yes, sir.
Fine, isn't it? So let me call that unique solution as phi2. Okay. And again, please remember that I am not writing down everything here. Please listen to it carefully, and please, you write down the proof on your own. Okay. Anyway, the recordings are going to help you. Okay. Fine. So let your let phi2 x be let me write it a solution of 2. Solution of 2. Okay. right? Then what must happen? Then what must happen? Your this phi to x1, it must be equal to y1, isn't it? Right? And again, let phi to x be a solution of 2 in the interval, say this. Okay, so then I must have this equation. Then I must have this equation. Is it okay? Fine. And so that means what we have got, we have got phi 1 x1 equal to phi 2 x1. That has to be there. Okay. So now let us try to construct this phi 2x. Okay. See, this one was my x1. Okay. So then what I can do, I may take this, say, this is my, say, h2. Okay, so then what is going to happen? Somewhere, right? If this is h2, okay, so then this point is going to be x1 minus h2. Is this okay? This is x1 minus h2, right? And this point is x1 plus x2. So far so good, right? Now what we have to do, like let me continue. See, I'm not overlapping it so that it remains distinct for you. Although it is an overlapping curve. See, now you look at the interval of definition of the solution of this initial value problem 2 in this interval. Okay, so this interval is nothing but this interval. Okay, so what is going to happen? Your solution is going to extend, like it is going to be something like this, right? Something like this. Okay? Sorry. Yeah, from this point. Is it okay with everybody? Fine. Say the yellow curve is phi 2x, okay, and the violet curve is phi 1x. Is it okay with everybody?
Yes, sir.
Yes, sir.
Right? So that means what we must have, the overlapping, it is occurring in the interval this. Okay, fine. So what must happen in this phi 1x and phi 2x must agree. Fine.
Yes, sir.
Okay. See, phi 1x and phi 2x must agree in order for having a common solution in the bigger interval given by this. Is it okay? Say suppose phi 1 and phi 2 didn't agree in the interval. Phi 1 and phi 2 didn't agree in the interval. What is going to happen? I have a solution in I1, okay? I have a solution in I2, right? But I cannot claim that I have the same solution over the whole bigger interval x0 minus h1, comma x0 plus h1 plus h2. Are you getting my point? Had they not agreed in the interval, what would have happened? I could still get two different solutions in those two separate intervals, right? Isn't it? But I cannot get the same solution over the entire bigger interval. Is it okay?
Yes, sir.
Yes. So that means I could have, if this happens, I can have. See, I'm still saying I can have or I may have. I'm not saying that I must have. Okay, I'll tell you, I mean, why I'm not so confident about that. Okay, fine. This must agree. Thus, we may be able to find a solution of the IDP1 over the interval this one, x0 minus x1, and if I write it, okay, let me write it so that, okay, and of course this x0 plus x1, it is by this x1, okay, given by, understand, find a solution, let me call it, find a solution phi x, given by something like this. I am going to define it piecewise. So this is equal to phi 1x when your x lies in the interval x0 minus a, sorry, x0 minus h1 x, let me call it x1. Okay, rather than writing it x0 plus h1, I am writing it h1, x1. Is it okay? Right? And this is phi 2x when this, I can simply call it this h2. Okay? Fine?
Yes, sir.
Is it okay? I can have a solution like this.
Yes,
See,
sir.
there is a possibility of having a common solution if, like, obviously they have to agree, both phi 1 and phi 2, they have to agree in the intersection of these two intervals, right? Okay, so we are almost done. Only thing, see, we have got a function, right? We have got a function phi x. So now, if I have to claim that this is the unique solution over the bigger interval, given by this, right? Then what must happen? You look at the point, I mean, x equal to x1. What must happen at x1? Yes?
Phi 1 x1 is equal to phi 2 x1.
That is already there. Apart from that, where did you get the differential equation? You got the differential equation from the derivative, isn't it? Fine. You must be able to define the derivative at the point x1, because that is the crucial point. That is the juncture of these two functions, your phi 1x and phi 2x, right? So that means the left hand derivative and the right hand derivative of phi must agree at the point x1. Is it okay with everybody?
Yes, sir.
Fine. So that is what we are going to do now. Okay. Fine. So, and again, say this you have to, although I haven't written it down, I mean, in your proof, you please write down all this thing. Okay, the derivative must agree. In fact, I have written it down somewhere. So maybe what I am going to do, I'm simply going to scan my handwritten pages and I'm going to hand it over to you. Okay, fine?
Hello, sir.
Yeah, I'll upload in my extra material section.
Sir, can you give an example of this last query, what you told, that proving all these theoretical concepts, then we can find an example where the derivative doesn't exist at this point x1.
No. If the derivative doesn't exist at the point x1, then you cannot get a solution. No, you cannot get a common solution. Definitely no. The derivative has to exist. The
But
derivative has to exist, and it will exist under these circumstances. Under the conditions that your fy, right? F comma and first order partial derivative with respect to y. I mean, they are continuous in R because we have already assumed that your what it is your x1 y1 that point also belongs to R. Of course, if that doesn't belong to R, we cannot define a new initial value problem. Okay, and here itself you will see that the continuity of f is going to guarantee that. Okay, fine. Okay, so now your this limit x1 plus I your okay, is it going to define? No. I'm getting it wrong. Sorry. Because I'm defining it in terms of this. Am I going to define it like this? Is it going to work?
sir, I think x goes to 0 if you want to define the derivative.
Is it going to work? I think
No, sir. I
is not
think
going
it tends to 0.
it is yeah. X1 tends to 0 plus. No, I'm thinking whether I'm going to define it this way or sorry about this.
Sir, phi of x minus phi of x1 by x minus x1
Phi of x
minus phi of x1.
no, I'm not going to do it that way. That's because I am interested at the location x1. I am interested at the location x1. Okay. No, and this should I? No, I'm just thinking. No, this is definitely going to be x1 because I'm going to do there only. No, I am just interested in like say what variable I'm going to use here. Should I use x or I should use some other symbol? That's my way. Now, is it going to make? See, if I write C, will it be okay? If I write like this, it should be okay, right? Yeah, then it will be right.
Yes, sir.
Right? Let us write it like this. My only concern is that x can create problem, but I think it is okay. Fine. Okay, fine. See, now you remember, like here in the whenever we take a point to the right of x1, right? I am going to consider the function phi to x, isn't it? Is it okay?
Yes, sir.
Yes.
Yes,
Fine.
sir.
Okay, so this is going to be limit x tends to 0 plus. For this, I can simply write. I can simply write your phi 2 x1 plus x. And see, for phi x1, whether I write, I mean, phi 1 x1 or phi 2 x1, it doesn't matter. Isn't it?
Yes, sir.
Right? So, I will simply write phi 2 x1. Okay? And what is this? This is simply is it okay? isn't it?
Yes, sir.
Fine. And phi 2x was the solution of and it was the solution in this interval, isn't it? I mean, x1 minus, fine. Okay, so your phi 2 prime x1, it must be equal to f of x1, right? Phi 2 x1, isn't it? If I go by the initial value problem 2,
Yes, sir.
yes, okay, fine. But phi 2 x1 is equal to phi 1 x1, isn't it? Phi 2 x1 is phi 1 x1. So I can write it as phi 1 x1. Okay, fine. And what is this? This is nothing but your phi 1 prime x1, isn't it?
Yes, sir.
Yes, sir.
Yes, right? Now you see phi 1, that function, it was a solution in the original interval x0 minus h1, x0 minus h1, comma x0 plus h1, right? So obviously at the end point of that interval, x0 minus h1, x0 plus h1, right? This is the end point. This is the x1, right? So the derivative that you are going to define there, it must be the left hand limit of the derivative. I mean, it must be the left hand derivative, isn't it?
Yes, sir.
Yes.
Yes, sir.
So it must be the left hand derivative of the function. Anyway, so let us just write it like just. I see where I took it from the proof there, they didn't write it down, but let us write it down that way. So it will be better. So this is limit x tends to 0 minus, okay, then let us write x1 plus x minus. Yeah, fine, right? So this is nothing but the left hand limit. So we have proved that the left hand limit is equal to the right hand limit, right? So obviously it is going to guarantee you the continuation of the first order derivative of phi over the entire interval, okay, fine. So that means we can definitely extend the solution to a much larger interval, okay. So see, this I was talking about the points, all the points that are going to be towards the right of the point x0 over the x-axis. Is it okay? Fine. By a similar argument, we can also extend this interval towards the left hand side of the original interval. Is it okay? Fine. Isn't it? So in this way, there is a possibility of extending this interval. Okay, fine. So, and again, you please, write it down systematically, the proof of this. Okay, although I'm going to give you but the way I have described it, you may not get all the information whatever I have written. Okay, so please do it according to your own convenience. So now let me show you the extension of this theorem. Okay, fine. So here you can see what they have done. Here in this theorem, they are considering R to be an open rectangle in R2, and of course they are assuming that your f of xy it is at least what continuously differentiable up to first order, okay, in R. So then for all x naught, y naught lying in R, of course, this is going to be considered as the initial point. There is a maximal interval J on which the initial value problem 1. So this is the initial value problem 1. It is going to have a unique solution phi x. That is, if the initial value problem has a solution psi x on I, then your I is a subset of J, and your psi x is going to be phi x for all x belonging to I. And again, this is very important. The next line is very important. Furthermore, the maximal interval is open. Okay, so that is what we are going to do. We are going to consider the maximal interval J to be something like an open interval alpha comma beta. Can you tell me why this maximal interval is open? Why it cannot be closed? Just give me one reason. Yes.
I think so. There will be some point where this condition will not satisfy. So we have to take the left open of this.
Okay, that is fine. So basically, I mean, at the at the point beta, at the point beta, there is a possibility that you would be able to define the values of the function f or its derivative only for beta minus. Similarly, at the point alpha, right? You should, I mean, you would be able to definitely define. You would be able to definitely define the right-hand derivative, isn't it? That is one. Okay. And what about just like I mean, citing some example? Can you tell me why? Cite one example and then tell me why it has to be open again. See, whatever example we took the other day, you have seen that, like the interval. See, I have taken the interval minus 1 to 1 as open interval. I could have taken an interval minus half to half as a closed interval. That I could have extended to the whole real line, isn't it? A whole real line, it is always going to be an open interval, isn't it? Right? You can give that argument also. That is also possible. That is also possible, isn't it? Fine. Okay. So now look at the corollary. So I'm going to do a couple of exercises for this corollary. Okay. You please have a careful look at corollary. Okay. So what it is telling you, let me explain it to you. So okay, so I'll just explain it. Okay, fine. So what it tells you, okay, say suppose I have the initial value problem 1, and then suppose I is the local interval. Suppose I is the local interval. This is the local interval. Okay, and suppose J is the global interval. Suppose J is the global, or it is the maximal interval. It is the maximal interval. Okay, so then what the corollary is telling you is that if suppose your yx, if yx is a solution of 1, okay, and if your beta is less than infinity, and of course alpha is greater than, hey, this symbol please don't confuse, huh? Don't confuse this. This is alpha, huh? This is alpha. Okay. So then what is going to happen? If you take limit of yx, say suppose as x tends to beta minus. So if it is equal to L, so you may have this possibility, or say you may have this possibility. Say beta tends to x your alpha plus y. Say suppose this is equal to x. Okay. So then what is going to happen? This N K J must be the boundary point where in the original, see here, this problem we defined in such a way that your Fy, they are continuous in an open rectangle R. Okay, so what this corollary is telling you is that, so if you find these two limits are always going to be a part of the boundary of R. That's what it must lie in the boundary of R. These two limits. Is it okay? I'll do a particular example, then it will be clear to you. Okay. Okay, consider this problem. Yeah. Yeah, can you tell me? I mean, here, say here, f of this, right? Is it okay? Right? So obviously, your Fy, they're continuous where?
Whole real line. R square.
Whole
Whole R2, right? Isn't it?
Yes, sir.
Yes, sir.
Right? Whole R2. Okay, fine. So now, if you want to solve this, what you are going to get? Can you give me the solution, please? Yes? Has anybody found out the solution? Yes?
Y equals to 1 by 1 minus x.
Y equal to 1 by 1 minus x. Okay? So that means what is going to happen? What is going to happen? It is defined. The solution is defined where?
For x not equals to 1.
So basically it is minus infinity to 1 or
Union
1 to infinity.
1 to infinity.
Okay, so you can take the maximal interval to be either one of them. Is it okay? Fine. So now let me. Yes. So let me try to do this. Yeah.
1 to infinity we cannot take because initial point is not there.
Great. Is it okay with everybody?
yes, sir.
Right? So what we
Yes,
must
sir.
do? What we must do that although f and fy it is continuous in the entire here I can don't worry about it. Here this r I can take it to be the whole r2, no problem about that. Yeah, because r2 that problem that is going to come in. Okay, fine. See, you guys yourself have found a way how to eliminate those intervals. Is it okay? Fine. So obviously, because this is not a, I mean, the point, I mean, 0, 1 or just a minute, just a minute. Is it 1?
Sir, only-
Is it because of 1 or 0?
Only 0, sir. 0
It
is
is
Or
not.
0.
It is 0. See here, obviously, your 0, it does not belong to this interval. Isn't it? It doesn't belong to this interval. So this is going to be my maximal interval. Okay, fine. So now let me take x tending to beta minus. So that means your 1 minus. Okay, fine. So if you plug this in here, you are going to get infinity, isn't it? Of course, although I am writing it as equal to infinity, in fact, this is in fact not a very good thing to write like that, but many books they write like that. Okay, it is going to tend to infinity. Is it okay?
Yes,
Fine.
sir.
Now you can see that infinity lies on the boundary of this arc. Is it okay? Fine. I'll give you another example. You just try that at home. I'll give you another example. You consider this one. You consider this one. Y and your y0 equal to 1. You consider this order and do the same. Like you prove that either, I mean, limit x tends to beta minus or limit x tends to alpha plus of the solution, whatever limit you get, that is going to lie on the boundary of that open rectangle. Is it okay? Fine. So with this, I am going to wind up about this continuation of solutions. So now, let me come back to your very easy quiz one. Okay. Now remember that you guys are no longer undergraduate students. You are not even studying MSc. Now you are PhD student. Okay, fine. So in my quiz one, number 1 was orthogonal trajectory. Number 2 was proving or giving an example, right? Giving an example in such a way that the initial value problem doesn't satisfy the condition of Picard's theorem, yet it possesses a unique solution. And I told you to give the initial value problem as well as the Lysis solution as well as the interval of definition. Okay, and probably the easiest was number 3. Okay, easiest was number 3. What was that? Fine. Okay, this was the problem I was giving. And what did I tell you? That
To find those x naught, y naught such that it has a unique solution in the neighborhood of that point.
that one. Okay, good. Okay, fine. Anyways, this was pretty straightforward. But let me tell you, I think somebody, whether he or she has realized or not, like just he or she got very excited, and instead of doing it for equal to 1, somebody was trying to do it for 0. Has anybody realized the mistake? Hmm? Has anybody realized the mistake? Don't do this kind of silly mistakes. Okay, don't do this kind of silly mistake. Even, I mean, some people are struggling with eliminating c square also. Okay, that is one thing. The next thing is that, see, I had told you to, I mean, give a rough sketch of the orthogonal trajectories, and it is like, say, you know that it is obvious that if I have a, I mean, what I have an ellipse like this, the orthogonal trajectory will be something like this. Okay, something like this. But it doesn't necessarily mean that this part is also going to be another ellipse, isn't it? You have to give justification for that. And again, now since you are PhD student, so not only for your, I mean, c square is greater than 4, c square is less than 4, you have to give me explanation for c square equal to 4 also. One or two people has given that. I'm very happy about it. Otherwise, you are not going to give full mark or get full marks. Remember that. Okay. So just by looking at the question that I mean, it is very easy, and your quiz one was very easy. It is not going to help. Okay. You have to be very precise about answering the question. Okay. Please don't jump into conclusion immediately. Okay. And again, this second one, I was very happy that I got 2-3 answers where they have given me this one. This exactly I discussed in class, but this problem I didn't explain anything about I mean, Lipschitz condition or it satisfying the condition of uniqueness and existence. Okay, so basically you didn't have to look for any other way. And again, many were trying to do something like your u1x minus u2x whole squared, something like equal to gx. Okay, and from there you were trying to prove that gx is simply 0 by claiming that it is monotonically decreasing. It is monotonically decreasing. It's first order derivative is always positive, right? You were trying to do something like that, okay? But I fail to understand. I mean, how can you claim something like this? Say, this is positive, and then you have u1x, u2x here. So, what is the guarantee that this is always going to be positive? I want the explanation for that. Nobody has written that explanation. Isn't it? In order for something like this to be negative, I know that, okay, this is positive. But what is the guarantee that this is going to be positive? I know that u1 and u2 individually they are positive. Okay. But how can you be sure that their square root is going to be positive? I could take the negative square root. Why I am eliminating the negative square root? Can you tell me? So you have to give me explanation for that. Okay, I see. Probably that is true. Probably that statement is true. But the thing is that you have to give me explanation for everything. Okay, and again, simply saying that it is monotonically decreasing isn't going to do. You have to give me explanation. Otherwise, I'm not going to take it. See, just I mean, looking at the problem, and then probably you have come across it before and got very much excited. And then, like writing down the answer like this, it is not going to do. You have to give me precise explanation for everything. And I have written at the top of the question paper that you have to give explanation for everything. Okay? I hope in future you are going to remember it. And many people, I mean, they were so excited about this one. What they did, they didn't write about the initial point at all. I mean, if the initial point is not there, how can it be initial value problem? Okay, fine. That is about 2 questions. Okay, so now let us come to question number 3. Let us come to question number 3. And don't think that I'm a miser in giving marks. I'm very generous in giving marks. Even I sometimes give half, even 1/4 also I give as marks. Okay. But the thing is that since you are PhD students now, expectation is more from you. Okay, fine. And so, okay, everybody, almost everybody got it right. Almost everybody got it right. Okay, now, what was happening? Question number 1 and 2. I think they carried 3 and 3 marks, right? And question number 3, it had 4 marks. Is it okay? Fine. Then you were thinking that, okay, like I am going to find x naught, y naught, okay? So you have already found out that fy, okay, it is not defined at the point, say, y equal to 0, right? So if I define a rectangle, this in R2 in such a way that your your x minus x naught less than equal to h, y minus y naught less than equal to k, right? Such that 0 does not belong to this y naught minus k, y naught plus k. My job is done. Yes, fine. And some of you have written it beautifully. I agree with that. Some of you have written it beautifully. But look at what is in stake, right? This particular question has, it is like maximal interval of existence, right? It has the highest mark among all the 3, right? Do you think that I am going to give you, see, these observations everybody knows who has studied uniqueness and existence theorem or who have attended my classes. But do you think that, because you should also know that I have to differentiate between I have to find out the good students from the bad students. Okay, how I am going to do this, right? Your intelligence will be reflected by how you have answered to these questions. Okay, so if you simply stop it here, then I'm afraid I'm not going to ever do the full 4 marks. I need more. What could be that more? Can you tell me?
So I think we have to find the value of h by this concept of minimum.
Something like that. H or k, something like that. You have to give me, or you have to give me something extra. Like say, probably you have to give me something, an interval. You have to give me an interval where the Lipschitz condition is always going to be satisfied. Okay, so basically, at least you have to give me something extra, because this part everybody knows. Can I? The question in your brain should have been: Can I give something more concrete? Isn't it? So I'll give you something more concrete. So what could you have done? You could have simply, giving me the Lipschitz condition. You could have simply given me the Lipschitz condition, right? Say, suppose if you take this k greater than 0 in such a way that it is small enough, in such a way that obviously y not equal to 0 you are going to take, right? So in such a way that 0 does not belong to this. So then, if you go for the Lipschitz condition, then what is going to happen? It is going to be, not even this. Okay, fine. xy1 minus f, xy2, right? Okay, so because 0 is not a part of that, where your y1 and y2 belong, so definitely, like say, I can have this, right? Y1 minus Y2, okay? And where of course Y star lies between your Y1 and Y2, okay? And what would be this? This is going to be your 1 plus Y1 star to the power 3 Y1 Y2, right? And since your Y1 star is not equal to 0, we have already chosen, right? We have already chosen my y's in such a way that it cannot be equal to 0. So this function, say suppose I consider this function to be phi y star equal to 1 plus y star to the power 2 by 3. This function is definitely going to be continuous in the bounded interval. Your y0 minus k, y0 plus k. Right? Sorry, not bounded interval, closed interval. This, right? So its continuity in this closed interval is going to guarantee me the boundedness. So there is a positive number, some capital M, such that this is less than equal to M. So I am going to get something like this, and this is nothing but ellipsis condition. That's it. See, you have to give me something extra, and let me guarantee you that nobody has got more than I think 1.5 mark in question number 3. So, so this is a lesson for you. Be careful in your future answers. Okay, don't think that I have kept the question paper relatively easy, so that this is your first exam in the entire semester. So at least I should give you some leverage. But that doesn't mean that you should be careless. Okay, so from now onwards, you be very meticulous about writing your answers. Okay, fine. And again, only 15 students have turned up their answer scripts. Like say somebody was, some people are not able to upload it there. It is fine. They have emailed it to me. But amongst all of them, I have been able to retrieve either from there or through email only 15 answer scripts. So, like, is there anybody who tried to upload but it didn't go through? Right, those who are attending my classes in today's class, did everyone turn up? Yes, or somebody didn't appear in the exam? Can you tell me?
Sir, I mailed you my answer script.
What's your name?
Sulakshna.
No, I got I got it. Yeah, I got your team. But there's somebody called Kannan. Yeah, I didn't get your mail.
Sir, I send you a mail, sir. I sent a mail, sir.
Did you send a mail?
Yes, sir.
What is your full name?
Kannan R. Mail ID is rkannan@gmail.com. Sorry, rkannan@iitgac.in.
But I didn't receive your email. Can you send it again?
Oh, okay, sir.
You send it immediately after today's class.
Oh, okay, sir.
But don't add. Don't add anything extra. I'll be able to figure it out.
Okay, sir.
Okay, because I was concerned about you because I have seen you attending my classes. You sent me mail earlier also, but I didn't get it in Teams app as well as in email.
Okay, sir.
I'm sure you didn't get any reply from me, right?
Sir, I get a reply, sir.
You got a reply?
Yes, sir.
Then how come I was? You still resend it to me, okay?
Okay, sir.
Your email may got lost somewhere, but anyway, don't worry. You please resend it to me. If I can retrieve your old mail, that will also don't worry about it. Okay, I just want to make it sure that nobody is late. Okay.
Okay, sir.
Okay. You please send it. Don't worry about it. If you have sent it earlier, but again you resend. I didn't get it. Okay. Fine. So now the next thing what I'm going to do, I've just put another 5-10 minutes and yeah, just this uniqueness and existence theorem. I want to rope in. Okay, see, many a time, if first order differential equation, what you do, you okay, suppose you have it can be given in this form as well. It can be given in this form as well. Okay. So then, what guarantees uniqueness of first order differential equations like this is that your this px and qx, no? They have to be continuous. They have to be continuous in an open rectangle. In an open rectangle, which contains this point, which contains the point x0, y0. Okay. So earlier, see, earlier what happened? Earlier it was like say both f and fy, they have to be continuous, right? So but now instead of that, if px and qx, pq as a function of x are continuous in an open rectangle containing the point x0, y0, so then this initial value problem, has a unique solution in the neighborhood of the point x0. Okay, and it is pretty straightforward. The proof you can see here, f of xy, so this is equal to minus pxy plus qx. Okay, so obviously since px and qx are continuous functions, and y itself is a continuous function, right, in R. So obviously this product is going to be continuous, and eventually this expression, it is going to be what? It is going to be continuous in the rectangle R, and obviously you know that. I mean, if you find out the partial derivative with respect to y, it is simply going to give you minus px, which is again continuous. Is it okay? Fine.
Yes,
Okay.
sir.
Yes, and again you can do it through this Lipschitz condition also. Lipschitz condition also, it is going to eventually you are going to get your f xy1 minus f xy2, because this is going to be eliminated. You are going to get it as simply okay, right? Since I am considering px, in a closed domain, isn't it? Right? And I am already assuming that P is continuous in the open rectangle R, which is, I mean, not, it is a bounded domain. It is a bounded domain, right? So then what is going to happen since it is bounded? So obviously by the boundedness of the function P, I can always prove the Lipschitz condition here. Okay, so that is why yeah, under these conditions that Px and Qx are continuous in that open rectangle containing the point x0, y0, I can have a unique solution. I'm going to have a unique solution. Okay, so I am going to start your second order differential equation in my next class. Okay, so some of the concepts that you have already learned, I mean, they are going to be repeated. My first class is going to be about the fundamentals. Okay, and then I'm going to move to the theorems involving Wronskian, and probably the series solution. I'm not going to go in detail, but I'll be more interested in system of equations where we are going to study this autonomous system, all those stuff, where a system is stable or not. So basically, the dynamical system concepts, I mean, you'll be introduced to that, and I'm going to emphasize more on that. Okay, fine. So maybe I'm going to meet you tomorrow. Okay, fine. And please remember that the next Saturday there is no class. Okay, and in the next month I have only one class on Saturday. Okay, I'll let you know. which Saturday it is. But next Saturday there is not going to be any class. Okay, fine. So I'll meet you tomorrow.
Sir,
Yeah.
sir, I got it to when I do a for problem in our assignment sheet for